My name is Valentin Goverdovsky. I come from Imperial College London. I'm postdoc there at the Communication and Signal Processing Group. And I'm going to talk about something we call hearables. Okay, so first I'm going to briefly introduce our relatively small group and who we collaborate with on this project. I will then move on to describing why you should care about hearables and wearables in general and what the story is so far. And then I will introduce the technology that we are working on right now, which is the ear-worn brain and body monitor, and finally present some of the challenges and our vision for this technology. So we are essentially two research groups across two universities, one Imperial College London and the other one is the Aarhus University in Denmark. Why these two universities? Well, essentially the idea about the ear-worn sensor has been spawned by a discussion between the two group heads, Professor Danilo Mandic at Imperial and Preben Kidmos, who at that time was working for Widex, which is a fairly big hearing aids manufacturer in Denmark. And the idea was to come up with a smart hearing aid, because right now, if the hearing aid settings have to be readjusted, then the person has to go to the clinic, and it's a fairly laborious process. So they wanted to monitor the activity of the brain and adjust the hearing aid on the fly. So right now we're also collaborating closely, depending on the experiment that we're running, with different units in different hospitals. For example, sleep unit at the Royal Brompton Hospital, Imperial and Hammersmith Hospital for brain trauma, and also Royal College of Music on the performance science, because we find that live performances are a very good platform for evaluating a lot of the technology, because it's essentially a controlled environment within the real world setting. So why should they care about the wearables? Well, we believe that wearables will allow us to bring healthcare from reactive model into more and more preventative model. And we hope that we're going to see less and less of people who are hooked up with wires when they undergo a variety of tests. So this particular gentleman is going through a sleep study, so he has to be hooked up to a number of sensors on the head to measure the EEG. Then he has ECG, which is the cardiac activity. His breathing is also monitored, and he's expected to sleep with all of that. And obviously that is virtually impossible, and you do get biased results, etc. So we're also hoping that it's going to make the life of the chronically ill patients easier by allowing them to continuously monitor, for example, blood sugar for diabetics, etc. And also provide critical information in some of the high-risk environments for example, drivers on the road when they're feeling fatigued or stressed, and that can affect the performance. And also pilots piloting the airplanes. So, what is the story of the wearable so far? Well, there has been a huge explosion of different devices in the recent years. There are loads of fitness trackers. The majority of them employ essentially a single chip which integrates three major sensors: accelerometers, magnetometers, and gyroscopes, and that gives you the activity level and the position of the device within three-dimensional space. But there seems to be a bit of a problem with those devices in terms of the fact that they are worn for a fairly short period of time and then they are quickly forgotten. And because ultimately they don't necessarily provide recommendations or some actionable items to the people to act upon. Also, there are research devices that cost thousands of pounds because ultimately they have to be medically certified, and that's a fairly laborious process. Then there are some devices that are integrated into the apparel and accessories, and that seems to be a very promising approach, because those devices, in addition to monitoring the physiological parameters of your body, they solve a slightly different job to be done as well. They are a fashion accessory, so you would wear them anyway. If you want to make a statement or you want to have a sort of a luxury good on you, then those devices will be on you, and they will be solving multiple jobs to be done simultaneously. Unfortunately, among all of these devices, there is no compelling solution for monitoring the activity of the brain. All of those, they monitor the essentially the mechanics, or they monitor the cardiac activity. So to monitor the brain, usually we use something called electroencephalogram. And to get an electroencephalogram, you have to place a large number of electrodes along the scalp, and you have to connect those electrodes to a static unit, which is fairly bulky, and you can not lug that one around with you when you do your daily activities. There are several new devices, for example, the Emotive or a Minto kit. Those are wearable. They have a wireless interface, but ultimately, even those, you don't want to be wearing them in the like in the real world, really. So they are somewhere in the boundary between the laboratory and the real world environment. So the idea that we have is to integrate the EEG sensors as well as a variety of other physiological sensors on an earplug. So in much the same way as you wear headphones, you would be wearing this device, which will monitor your brain activity as you, for example, listen to music. In the end, ultimately, we also envisage this technology to be completely in the ear because, for example, there are hearing aids right now that can be placed inside the ear canal and they can work for a reasonably long period of time. They're completely inconspicuous, and wearing them does not provide any real drawbacks. So what are the applications of the ear EEG sensor? Well, there is a huge variety of these. There is a number of different responses that you can measure from the brain. One of those is, for example, the auditory steady state response, and that is the brain signal that is produced when the person is hearing a particular sound. And based on the measurements from the brain, you can get a hearing threshold, and you can use that hearing threshold to adjust the hearing aid. Then there are steady-state evoked potentials, and those are produced when the person is observing a particular visual stimulus, so a blinking light or a blinking part of the screen. You probably have seen some of the demonstrations of the virtual spellers, which are the brain-computer interfaces where people who cannot move, they wear the EEG cap and they stare at the screen with blinking letters, and depending on which letter they concentrate on, we can pick up the signal and then select that letter for them to be able to type and communicate. There is a variety of other applications with regards to fatigue, for example, detection, and also the assessment of the quality of stress. These are some of the experiments that we are conducting right now with our collaborators. And also, we hope to be able to detect the early signs of brain trauma, for example, in the high-impact accidents, like in the Michael Schumacher accident, where he knocked his head on the stone, but he was still conscious for 15 minutes. But no one knew whether his condition is going to deteriorate significantly or he's going to recover. So these are basically some of the results of the experiment that we have conducted with the ear EEG electroencephalogram technology so far. And the left one is for detecting the fatigue. So we asked the subject to sleep for only 4 hours the night before the experiment, and then they had to come in and do a fairly laborious process of and fairly monotonous in a fairly monotonous task where they had to click the button when they saw a particular stimulus. And as we monitored the brain signals, we looked at the activity in the alpha band, which is the particular frequency band in the signal, which is from 10 to 15 hertz. And as the power and the variation of the power in the alpha band increases, the person was starting to make more errors. Now, how much of a lag there is between the errors creeping in and the increase in the alpha band, that's still debatable, but ultimately we can detect fatigue with this technology. This particular picture is showing the frequency domain signal that we measure from the brain once again when the person is observing blinking LEDs, and by assigning a context to each one of those LEDs, we can implement virtual spellers. And in fact, that has been demonstrated recently by one of the collaborators at EMBC. And finally, so this is the hearing threshold estimation, where we once again play different sounds at different sound pressures, and we can then map the response and the signal-to-noise ratio of that, which is going to indicate how well the person is hearing. So I have talked so far primarily about monitoring the brain, but obviously this platform can be used to integrate a variety of other sensors. So we have tried doing that by putting a mechanical sensor in addition to flexible electrodes. So what we have done, we had a flexible electrode and we placed a tiny microphone right behind it. And we placed all of that on the ear plug, which was placed inside the ear canal. And the ear canal pulsates ever so slightly as your heart beats. And that pulsation can be detected with the mechanical sensor. So therefore, you can extract the cardiac signal essentially from the ear as well. There are research groups that have shown that it is possible to embed PPG sensors, the photoplethysmography sensors, which are exactly the same as used in the Apple Watch, to get, for example, blood oxygenation and heart rate as well. You can also embed accelerometers, gyroscopes, magnetometers on that platform, and temperature sensors. Obviously, right now, all of those devices, they have their own packages, and they are not necessarily at the small enough level to be integrated into a completely in-ear platform. But every year, the devices are shrinking, and we hope that at some point, they will be small enough to be integrated in this tiny device. So what are the challenges right now? Well, there are certain technical challenges. In particular, for example, there is a problem with offloading all of that data from a tiny device via a wireless link, for example. The wireless link is usually the dominant is usually the dominant component in terms of the power consumption. So therefore, improving the design of the wireless links is one of the challenges that has to be overcome. Then there is a problem with electrodes. When we do these experiments right now, we have to wet our electrodes ever so slightly with saline solution, which is pretty much salty water. But if we are to have these devices being used by general public, then we would want to have completely dry electrodes so that the person would be able to pick up the device and put in their ear and get the brain activity signal straight away. Then at the same time, there are obviously some other problems with regards to the data and the quality of the data. So the data, just collecting the data is not enough. We need context, we need the right quality of the data, we need continuity, and also just collecting more data does not necessarily mean better outcomes for the patients. And finally, there are privacy and ethical concerns with regards to what do we do with all the data that we collect, where do we store it, who has access to the data, etc. So there are still a lot of open questions. So our vision in general is that in the future we will be able to integrate essentially all of the sensors that can measure all of your vital signs on a tiny monitor that you would be able to put inside the ear canal and monitor the state of body and mind of yourself. Thank you.